We talked about heat energy, and we need a few properties of heat because heat will be a dominant form of energy in some environments that we talk about. And so it's a property of heat that if you have a hot object and a cooler environment, then the hot object will lose energy to the environment, and this process will continue indefinitely or until such time as the temperatures equilibrate, because as the source loses heat, the environment gains heat and warms up, and eventually, if the temperatures are equal, then we have equilibrium and heat flow stops. But so long as you have warm sun in cold space, the sun will continue to lose heat to space, and until such time as either space heats up or the sun cools down, this process will continue. There will be a constant flux of energy out of the sun into space. And there are several ways by which this transfer of heat from a hotter to a cooler body can occur. One is called conduction. This is where heat is transferred through continuous contact, and this is not in great importance. In astronomy, heat conduction on astronomical scales is rare. A second phenomenon is convection. This is basically like trucking. This is what happens when the physical motion of the fluid carries energy. This works very well if you have volume of fluid that is heated from below. That happens when you boil water on your stove. It also happens in stars, say, where a hot core is heating the atmosphere from the inside. What happens is that at the bottom of the pot or the bottom of the atmosphere, the fluid is heated, the heated fluid expands, the expanded heated fluid is lighter, less dense than the surrounding fluid. It therefore floats to the top and rises. Cooler fluid descends to take its place, and what you have is an energy transfer from the bottom to the top by heated fluid physically moving from one part to the other. And this does occur in astronomical phenomena. None of this, of course, is helpful to the sun in losing its energy to space, because the sun is not in contact with anything, nor is there any fluid around it to convect. The way the sun loses energy to space is radiation. It turns out that every object, unless it's at zero temperature, glows, and that mechanism of energy loss is radiation heat transfer, and essentially the radiation in question is sunlight. Sunlight is the way the sun attempts to heat up space, losing energy because it's warmer, and we'll come back to this calculation in a moment, but let's understand something about this heat flux, energy flux problem. And so the sun is hot, and so it radiates, and we'll learn how to compute how hot it is and how much it radiates. But for now, let's assume that the sun is radiating energy at a constant rate. Why is the rate constant? Because the properties of the sun are unchanging, the properties of space are unchanging. So the rate at which the sun loses energy to space is therefore unchanging. We call that rate the luminosity, and it's measured in joules per second, in watts. The sun, like a light bulb, produces a certain amount of energy, or loses a certain amount of energy to space every second, and we'll figure out this number. Obviously, it's a great many light bulbs. Now, what interests us often is how bright the sunlight is at some given location in space, and what that implies is put some uniform detector, say an eye with a fixed surface area, and as we saw, or as this diagram shows, if this is something the size of your eye or of your detector, the farther it goes, the less sunlight it traps, because essentially the sun produces radiation in all directions, and so at any distance, the sunlight is spread uniformly across the surface of a ball or a sphere of radius r. And if you are at some distance and you place your detector takes up some fraction of that sphere. If you are twice as far, the sphere is larger, and your detector now takes a smaller fraction of this larger sphere, and the result will be that your detector, since all of the sun's rays pass through this sphere, and all of the sun rays a little later pass through this sphere as well, the net total amount of energy passing through each sphere is the same, but the total amount passing through a fixed detector decreases because the spheres grow larger, whereas the detector does not. Mathematically, the statement is that at a distance r, the radiation is distributed uniformly on the surface of a sphere, so energy per second received by a square meter of detector will be the luminosity divided by the surface of a sphere across which the radiation is spread uniformly. And so the sun energy is diluted by a factor of r squared as it travels out into space. Light, of course, is going to be of incredible importance in our understanding of the universe. It's the main way we perceive our environment on Earth. It is certainly the main way that we receive information from distant places in the universe, so the properties of light will be extremely important to us.